What's going on, everybody? The networking guru here with Trepa Technologies, and today we're going over domain 5.2.1 of our Network Plus full and free video course. Like, subscribe, share with your friends, hit that bell if you enjoy this content, and let's go ahead and jump right into it. So I'm going to get my face out of the way here. So we're going over domain 5.2. This is our first section. We're going to be going over cable issues. So we're going to be going over everything from cable issues down to transmitters. In our next two videos, we'll hit these other major topics, interface issues and hardware issues. So first thing we got to make sure of, do we have the incorrect cable? Now, when it comes to fiber, we have two major modes, multi-mode and single mode. You can see here with multi-mode that we have a bigger glass core, which would be like 50 microns or 62.5 microns. I'm going to double check that in the post editing of this video. And that's going to allow multiple streams of light to pretty much bounce off each other. So the major thing to note with multi-mode fiber, yes, it has a larger glass core, it can propagate multiple light modes. This makes it more suitable for what we call campus installs. Its max distance isn't as great or as long as single mode. Now with single mode fiber, we're going to have that glass core that's typically going to be like 9 microns in size, and this is only going to propagate one light mode at a time, which means our single mode is more suitable for long haul connections. It can go up to 100 kilometers or more. Our deep sea cables go obviously a lot longer than 100 kilometers, and those are fiber. So, multi-mode, single mode. We have our glass cores, single mode being 9 microns, smaller. Multi-mode being 50 to 62.5, I believe, microns. And then, of course, we have that cladding around it, okay? We have the cladding around it that's going to protect our glass core. This leads us to about 120 microns for both multi-mode and single mode. Now, you may be wondering, well, how do we know the difference? Typically, single mode is going to be yellow. Now, the connectors can be the same. We can have the similar connectors, ST, LC. We have a lot of different types of connectors for fiber. But how we're going to differentiate typically is the color of the cable. Yellow is going to be single mode. Multi-mode is going to be orange. I'm going to pause the video and actually go ahead and bring in a multi-mode example here for us. So there's a multi-mode example. It's orange, but you can see the connectors are the same. They have the same connector types here. Just because this is brown, this is blue, doesn't matter, right? And this kind of gets into like transceivers as well. We have our SFPs, what we plug in to our switches and routers that have the SFP slots. We'll get into that. But they have the same connector types, but they're completely different, right? And that's to say that if I plug in a multi-mode SFP and then a single mode fiber in there, it's not going to work, right? Our hardware inventory is not going to recognize it. It won't be able to communicate. Okay, now moving on to copper. So Ethernet cables or copper cables are categorized by their performance specification, which determines their use in networking environments. So we have different categories here. So we have Cat5, not listed here. We have Cat5e, we have Cat6, Cat6 alpha, and then we have Cat7 and Cat8. I'm going to go back here. So with Cat5, our maximum data rate's 100 megabits per second, which is fast Ethernet. With Cat5e, it's going to be actually 1,000 megabits, which is a gig, right? Then with Cat6, our maximum data rate's up to 10 gigabits, supports distances of up to 100 meters. Cat6 alpha is going to be the same thing, 10 gigabits for 100 meters. The improvements, though, is that it's shielded. And that's something we're going to get into as well. Shielded versus unshielded Cat5, Cat6, twisted pairs, right? Copper cable. With unshielded, you're going to be more exposed to something like EMI or interference or signal degradation from something like EMI. Because what's going to happen is the copper signaling that's going in through those wires, there could be interference if we don't shield it from EMI from the outside. We'll get into that. Then we have Cat7 and Cat8. So Cat7's up to 10 gigs, 100 meters, improvements, individual shielding for each pair wire. So instead of having this like aluminum foil, tinfoil shielding around all 4 twisted pairs, we have it for each individual pair, which gives us even greater protection. Then we have Cat8 with a maximum data rate of 25 to 40 gigabits, the largest data rate for copper, but it's short distance, okay? High-speed data centers if you want to use copper. But yeah, primarily data centers where you maybe are just working in a single stack or maybe one rack over, right? So we can have those short distances. Okay, then we see unshielded twisted pair here. So you see this, just it's all exposed, right? So we have the jacket is what we call it, the jacket for our cables, and then just the copper. These are susceptible to electromagnetic interference and radio frequency interference due to the lack of shielding. This is the easiest though. Like if I'm at my office, I want to buy something cheap just to cable up my switch to a few cameras. And I'm not worried about like industrial systems with EMI and just EMI in general. I'm not worried about someone coming in, messing with my cables. I'm probably just going to use unshielded twisted pair. It's cheap and it's really easy to crimp, really easy to make. Now with shielded twisted pair, we're going to have that braided or foil shield here. We can even have foil shields individually around the copper pairs as well. So with shielded twisted pair, they have an additional layer of shielding, usually made of foil or braided copper. I've seen the foil a lot more. Braided copper probably a little bit more expensive. This makes it resistant to EMI and RFI. It also provides better signal integrity over long distances and noisy environments compared to UTP. So all things equal, if we're just running it across a field, UTP STP has the same distance. It's going to be that 100 meters. But again, like I said, if we're running it through an industrial area where we know there's a lot of potential interference, shielded twisted pair is going to be what we want to use. And in a lot of environments, that's kind of like the compliance thing, where we use shielded twisted pair because of that reason, and because of possible things like crosstalk, which we'll get into. Okay, so other cable issues, signal degradation. Degradation. Hopefully I'm saying that right. It occurs when the strength and quality of the signal weakens over distance or environmental factors. So we have distance, right? We have our 100 meter cap for copper, cat 5, shielded pair, unshielded twisted pair. But we have environmental factors. So we have things called crosstalk. So crosstalk is interference caused by signals in adjacent cables. It can occur when electrical signals from one pair of wires leak into another pair. Pretty much like, you see what we have on the screen up here? That may be susceptible to some crosstalk, right? Where we have those strong signal, but the signals in those copper, the orange-white, and then another orange-white pair, and then we wonder why are we not going as fast? Why do we have packet loss? Why do you have things like loss, right? Well, you may have some crosstalk there, okay? Interference. So interference from external sources such as fluorescent lights, motors, and other electrical devices can disrupt signals, especially in unshielded twisted pair. Obviously, shielded twisted pair or fiber optic, because it's light, are immune to EMI. Then attenuation. This is what essentially happens on our distance. Attenuation is the gradual loss of signal strength as it travels through a cable, and it's distance related, right? We see this in RF a lot too with like wireless signals. Attenuation's when we're losing as farther we go out, like in a 5 gigahertz network. If we just put 5 gigahertz in a field, a football field, in the middle, at the goalpost, we're going to have less signal strength. That's the attenuation because the distance. It happens in copper wires too. So the longer the cable, the more attenuation occurs. High attenuation can result in poor signal quality or data loss over long distances. Improper termination. So obviously, if you try to plug this example in here, it's not going to work, right? Now, we have crimpers that will like cut off the ends there that I don't actually really like. But we have to make sure we have proper cable termination. We want to make sure that our cables are terminated correctly and all 8 pins, all 4 pairs are level when we do our crimping. So in our academy, if you buy our academy course, one of my bonus videos is like going through this. Like, hey, this won't work. Doing the tests and stuff. But you can see this guy right here, or girl, it could be a girl's fan. If you go to put that in an RJ45 and go to crimp it, more than likely this blue pair and probably this orange pair won't reach. Or we'd have the opposite issue where the brown pair is going to go through. And then we may have some pairs that aren't able to terminate from end to end. So we want to make sure we have proper termination when we're crimping our RJ45 ends to our shielded or unshielded twisted pair copper Ethernet cables. Transmitter and receiver transpose. So in Ethernet connections, the transmitter, TX, on one device must connect to the receiver on the other. When these connections are reversed, transposed, data cannot flow between devices. So it's like TX to TX or whatever, right? The issue is especially common in Ethernet cables. It's typically resolved by using crossover cables or devices with auto-sensing ports. Crossover cables are kind of almost a thing of the past because something, at least in Cisco technology, and I think it's an IEEE standard, I'm not entirely sure, is we have that auto-sensing capability. It's called MDIX. Don't know what the acronym stands for off the top of my head, but it used to be like devices, router to router. you'd have to have a crossover cable, switch to switch. You have to have a crossover cable, right? Well, now it's opposite. We don't need that. You can just do a straight through cable is what it's called. Straight through cables are the T568 Alpha or T568 Bravo standards that are the same on each end, right? That's a straight through cable. Well, like devices don't need crossover cables anymore because we have that auto sensing. It's called MDIX. But if you didn't have that, some legacy devices, you're like, hey, my switch to switch isn't working. What's going on? You may need a crossover cable. Okay, so troubleshooting steps for cable issues. So identify the cable type, check for signal degradation. You can do that like on the CLI. You can do that with some testing equipment, like actual hardware. We want to inspect our termination. Again, we can do that. We can eyeball it. Your experience, you can do that, right? You've been doing networking for 10 years, cabling things up. But if you're not experienced, really, you can do it for a straight month. No, if you do that for 3 days straight, you can be able to tell when something's not going to work in a RJ45. But we have tools, right? We have Fluke, we have cable testing tools. And then confirm the transmit and receive alignment, right? Verify that the transmitter and the receiver connections are correctly aligned, especially on manually configured connections. Legacy, right? Okay, let's go ahead and do our quiz. All right, so let's go ahead and do our quiz. So question 1, which of the following issues could be diagnosed by observing an increasing number of CRC errors on a network device or network interface? So we didn't talk about this yet, CRC specifically. It's called cyclic redundancy checks. They're part of the FCS field in an Ethernet frame that ensures that all the packet's complete when it comes to a device, right? Or that we're not having sequencing errors, things like that. We're going to dive into it, I think, in the next section. But I guess we're a little early in this quiz. But that's going to be A. Physical layer issues such as faulty cabling. There's the explanation if you'd like to pause the video and read. Question 2. In a network troubleshooting scenario, which of the following would most likely cause signal degradation due to attenuation? That's going to be C. A 100-meter Cat5 cable run. So attenuation refers to the loss of signal strength over distance. Cat5 cables are designed to support up to 100 meters at 100 megabits, but at this maximum length, they may experience signal degradation. So they can do it, but you may experience some, because attenuation doesn't mean complete signal loss, right? And just to go down here, I think like multimode fiber for long distance WAN connections, obviously that can't be used, right? So you wouldn't experience degradation. It just straight up wouldn't work, right? It would just signal loss. Question 3. When diagnosing a network issue, you discover that the transmitter on one device is connected to the transmitter on the other device. What is the likely outcome and what is the best solution? So that's, if we have legacy equipment that doesn't do MDIX to auto sense that and reverse it, we're going to have no connectivity. It just won't work, okay? So you either use a crossover cable on our legacy devices, upgrade your hardware so they can do the auto sensing. Go ahead and pause the video if you'd like to read the explanation. Question 4. Which of the following cable types would be the most appropriate for a 10 gigabit per second connection over a 90-meter distance in an industrial setting with high electromagnetic interference? So we need 10 gigs, so the Cat5 options are out of there, even if they are shielded, which would protect us from EMI. Cat6 Alpha, Cat7. Cat7 could do it, but it's unshielded, which I don't even think they make, so it's kind of like, well, you only have one correct answer here, and that's B. Cat6 Alpha shielded twisted pair. You can go ahead and pause the video if you'd like to read the explanation. And then last question, what issue is likely to occur if a network cable's twisted pairs are untwisted too much during termination? It's going to be crosstalk. So remember, crosstalk is going to be signal interference from other cables. So when they're not twisted, they're not tight like that, and our cables near the termination, we're going to get that crosstalk, potential crosstalk, okay? And all right, let's view our results. That's 100%. I want to thank you all for viewing. If you like this content, like, subscribe. If you're interested in live virtual training or our self-paced course where you get all of our additional features in our learning management system, hit that link in the description below. Reach out to us. Thank you for viewing. I'll see you in the next video.